Okay, welcome back. What we're going to do right now is we're going to, of course, keep working through these questions. We've got up to number 16. In this video, we're going to be covering question 11 and 12 from the back of your book. So question 11 and 12 from the IB 2014 chemistry book. So this is the book that I use for my class. Basically, let's look. So this question, right? This whole chapter has to do with like enthalpy or energy change. Can't just enthalpy, energy change, and the different energy changes that we have to know. So question 11 states two different reactions. So it states one reaction: sulfur as a solid reacts with oxygen as a gas reversibly to form sulfur dioxide, which is a gas, and the delta H naught value is equal to negative 297 kilojoules. And it states the second reaction is that SO2, which is the gas from the previous question, reacts with O2 to form reversibly sulfur trioxide, SO3, which is also a gas, and the delta H value is equal to negative 92 kilojoules. So these two reactions are used in the manufacturing of sulfuric acid. And if you've done IGCSE, this was called the contact process. So if you remember, we reacted sulfur trioxide to oleum and then dilute oleum in water to release sulfur dioxide, or to release sulfuric acid. So you should, if you don't remember that contact process, it's worth reviewing because as you can see, that contact process is coming up again, even in IB. So it's not bad to review the Haber process and the contact process and the conditions, the conditions of the reactions. So the question states, it says, what is meant by the term delta H naught? And then it says, state whether reaction 1, or reaction A, and I'll put reaction B here, state whether reaction A is exothermic or endothermic. And then providing evidence. So to answer this, let's go down. So, you can pause the video right now and try to answer this question yourself, or just watch through, because I've posted so many other questions for you guys to work on too. So our delta H naught, what that was, right? That was the standard enthalpy change of reaction. A standard means that this is done. This reaction is done at 1 atmosphere of pressure and 25 degrees Celsius. So it's done under standard conditions. And the second one, the second part, so reaction A, is it endothermic or exothermic, and provide evidence. So you just need to look at the information that they give you, and you say, okay, reaction A is exothermic, and the evidence is just that the sign of delta H is negative, exothermic. The sign of delta H naught is negative. And as we all know, that negative delta H's means that the bond strength in this molecule is stronger than the bond strengths in these molecules, so it's more stable, and you shed the excess energy as heat in this case. Okay, so I'll go down a little bit and then react, question B, or part B. I'll change back to black for the question. So B, it says, at room temperature, sulfur trioxide is solid. So at room temperature, SO3 is solid. And then it says we need to compare it to this SO3. So at room temperature, sulfur trioxide is a solid. And it says deduce whether the delta H naught of this reaction, delta H naught of B, holy, there's just like a windstorm right now. So deduce whether delta H naught, which is reaction B, would be more exothermic or less exothermic. If this reaction above was going to the solid phase. So basically if this reaction turned to SO3 solid. So if SO3 solid was produced. So the way to answer this question, let's go down a little bit. So the way to answer this question is pretty straightforward, right? If we look at, if we just think about, even water, right? We've got these phase transition graphs where we've got a solid, a liquid, and a gas. And we know that we need to increase the temperature. We need to add energy in order to transition from a solid to a liquid, and in order to transition from a liquid to a gas. So if we were to transfer from a gas to a solid, we'd take away energy. We would lose energy, which means that we would release energy. So you lose energy to the system. So the delta H naught value would be more exothermic if SO3 solid was being produced directly, So SO3 would be, the delta H naught value of the reaction would be more negative. And then let's look at C. Let's finish off this question. Let's look at C. So with C it says deduce. So solve, basically. Solve the delta H naught of this reaction of sulfur solid plus 1.5 O2 reacts to form SO3 gas. So we basically, we need to use the information that was provided to us before. So I'll rewrite those equations down here just so that we don't need to keep scrolling up and scrolling down. So the first equation, I'm not going to put the state symbols in here just to save a little bit of time. I don't want you to be watching these videos all day. Forms SO2, and the delta H naught was equal to negative 297 kilojoules. And the next one was SO2 plus 1/2 O2 reacts to form SO3, and delta H is equal to negative 92 kilojoules. So this is an SO3. So okay, so we just do what we did before. We do the same magic, right? We just remake these equations so that they cancel off and equal this equation at the end. So we know that we need to end up with this final equation. So let's look at this. We need sulfur on the left-hand side. We need sulfur trioxide on the right-hand side. So we've got everything in place. And we might be able to just add these together, actually. It looks like we could just add, we could just add these equations together. So wow, it's already solved for us. So SO2 on the left and SO2 on the right here, they cancel off. O2 on the left adds to be 1.5 O2. Sulfur is the same, so sulfur, solid, plus 1.5 O2 reacts to form whatever's left on the right, SO3. So our delta H naught is equal to delta H naught 1 plus delta H naught 2, which is, let me do the calculation really quickly. Negative 297 plus negative 92. So our delta H of this final reaction is going to be negative 389 kilojoules. And that is our final answer to number 11. So now let's just work on number 12. Let's just finish up number 12. And that's all we're going to do for this video. And number 12 is a little bit of a quicker one anyways, so I'll change back to black for number 12. Back in black. So okay, let's do this. But1ene reacts with oxygen to produce CO2 and H2O. That's the information that they've given you before. And to do that, it's 4 and 4 to make sure that it's balanced. So I'll write down the chemical formula. C4H8 plus 6O2 reacts to form 4CO2 plus 4H2O. Oh no, H2O. So that's the reaction that we're looking at. And then it gives us the bond enthalpies. So anytime you're given bond enthalpies, you know you're going to have to do some sort of calculation. Average bond enthalpy. So the bonds that we're looking at is a carbon-carbon bond. We're looking at a carbon-carbon double bond. We're looking at a carbon-hydrogen bond. So that's a carbon-carbon double bond. We're looking at an oxygen double bond. Carbon-oxygen double bond. And finally, an oxygen-hydrogen bond. And those values are all in kilojoules. So this is in kilojoules, just so I don't need to write them down over and over. Just 348, 612, 412, 496, 743, and finally 463. So it tells us, you use this information to find out the delta H naught of combustion, to estimate the delta H naught of combustion. So let's solve this, right? We know that we need to use the formula for bond enthalpy, and to rewrite that formula out another time, like I have in the last videos. Delta H of reaction, delta H naught of reaction is equal to the sum of bonds broken, which is another way of saying reactants, minus the sum of bonds formed. So remember, this part is endothermic, and bonds being formed is always exothermic. So let's do this. Let's work our way through this question. So I'm just going to scroll down so we've got a bit more space. Maybe zoom out just so we got a little bit more space, because this might be a bigger question. And let's work. So we got to draw out the structures of these, right? We don't know what the bonds are without drawing out the structure. So if we were to draw out but1ene, meth, eth, prop, but, 1, and then we just draw all of our hydrogens in there. H, 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 H. And then to double check your answer, just make sure carbon has 4 bonds everywhere. 1, 2, 3, 4, we're good. 1, 2, 3, 4, we're good. 1, 2, 3, 4, 1, 2, 3, 4. So carbon's got all the bonds. Plus 6 oxygens reacts to form 4 CO2 plus 4 H2O. So now we can see what bonds, and already I've written in front of them the important information. How many, because we know that's the factor that we need to multiply by. We've got a 1 before here. We just can't see it. So we've got 2 carbon-oxygen double bonds. So that's 2 times carbon-oxygen double bonds, 743. And we need to multiply all of that by 4. Plus 4 times, and this is 2 oxygen-hydrogen bonds, so 2 times oxygen-hydrogen is 463. And then we're minusing that off. And let's look at this. This is going to be the complicated part. 6 times oxygen-oxygen double bond is 496. And finally, these are going to be our harder ones. We've got 1, 2, 3, 4, 5, 6, 7, 8 carbon-hydrogen bonds. 8 times a carbon-hydrogen is 412. Plus, we've got 1, or I'll change the color here. We've got 1, 2 carbon-carbon single bonds. So 2 times 348. Plus, and the only bond that we have left is right here, a carbon-carbon double bond. So plus 612, 612. And if we add all these numbers together, add all the left-hand side, add all the right-hand side, we'll come out with the right answer. So just let me do this calculation very quickly, and then we're all done. 2 times 348 plus 8 times 412 plus 612 plus 6 times 496. So on our reactant side, to break all of these bonds and make it reactive, we need to input 7,580 kilojoules of energy. But then we're minusing off the energy of the bonds being formed. So let's look at doing this. 2 times 743 times 4 plus 2 times 463 times 4. So this value is 9,648 kilojoules. So the energy of the bonds being formed is much higher than the energy of the bonds being broken. So this reaction is going to be exothermic. And if we do, we finally calculate the delta H value. Delta H naught is equal to 7580 minus 9648. 7580 minus 9648. We're going to come out with approximately negative 2,068 kilojoules of energy is going to be released. And that's kilojoules. Yeah. So that'll be our final answer. That'll be our delta H for this reaction. So let's just do the second part of this question, and then you'll be free. So it just simply says B, state whether the above reaction is endothermic or exothermic. So that's easy enough. You say delta H naught is negative. I'll erase that. Which means that energy is released. Therefore, it is exothermic. And that's it. So that's the end of question 11 and question 12. So join me again to finish 13 and 14.